Good afternoon, everyone. Welcome to the quantum computing course this term. I'm greeting you today from Sweden, where I'm for a short exchange, but I'll be back in Deggendorf next week and teaching the course this week here from Sweden. This course is about quantum computing, and we'll be exploring quantum computing as of today. First things first, these lectures are recorded, so if you make any audio contributions or turn on your camera, you will be recorded, and the recording will be available to all the other students. Ideally, just keep your camera off. I'll also keep mine off. And if you have any questions, you can turn on your microphone, which will then be recorded. However, you can also send your questions to the chat, and then I'll read out your questions without referring to you personally and answer your questions. So that's the update on the privacy. So if you don't make any audio contributions, you will not be part of this recording in any way. I teach this course together with Professor Kuhnhardt. He's probably not present today, since I teach almost all of the course. Professor Kuhnhardt only teaches 2 weeks of the course, probably the session in 2 weeks from now and sometime later in the term, but all the other lectures are given by me. And Professor Kuhnhardt will introduce himself when he teaches his first session in a few weeks, but I run the course and do all the admin around it. So if you have any questions on the course, ideally just get in touch with me. Quantum computing is a very fascinating topic, which has become more and more popular in recent years. And Professor Kuhnhardt and we started teaching this course, I think 2 years ago. So we're teaching it now for the third time this year. And we came up with this course because I teach the algorithms and data structures course, which many of you have probably taken before. And at the end of the course, I sort of had an outlook on quantum computing, since quantum computing heavily affects algorithms and complexity. And Professor Kuhnhardt turned out to be teaching an intro to quantum computing in his operating systems class that he teaches in some of our programs. And we both felt we wanted to do more, and then we came up with this elective. If you have taken previously my algorithms and data structures course, maybe just send me some sticker here or something, that I just see how many of you have dealt with that intro before. Many of you have also not. I'm aware of this because this class is open to many different degree programs and exchange students, but I also recognize some of the names that are here in this session. And then Professor Kuhnhardt and I felt we want to engage more in this topic and make it also more accessible to other students. And that's why 2 years ago we started this elective, and every year it's becoming more popular. Today, I will start directly with a motivation, what quantum computing is actually about. We'll talk about the organization of this course later today, and we will look into some of the mathematical foundations we will need for the rest of the term. And if you have any questions about how that course is organized, maybe just wait a little bit, because I'll talk about this later, but I don't like starting a course just talking about administrative details. So I actually want to motivate the topic, why quantum computing is so exciting. And I want to know from you, so maybe don't peek into the slides and see what the solution is to what I'm asking now. I want to know from you how you can speed up an algorithm. Say you implement an algorithm and the algorithm is just slow. If you have any suggestions how you would speed it up without looking into the slides, maybe send some of your suggestions here in the chat, and I can see how you would speed up a slow algorithm. We got one suggestion already: multiprocessing, meaning parallelization. We can use multiple threads, multiple processes. and with a modern CPU, we can speed it up. That's one good suggestion we got in the chat. If you have other suggestions, like one student says hardware upgrade, yes, you can get a faster computer. That's fine. Anyone has another suggestion?
Mit Kabel. Auch für die gibt es ein Kabel da drin.
Someone has his mic on, and we just got some noise from there. Okay. You're most welcome to turn on your microphone if you have questions or contributions. So there are more suggestions. Use like a low-level language like assembly. Use a data structure with exactly, I don't know, maybe that answer was not completed. Feel free to complete it. One student suggests to find another implementation which is faster. Yes. Or one student suggests reducing the complexity. That's good. Faster CPUs, GPUs, faster hardware. One student suggests to use, instead of iteration, use an algebraic method for computation. Okay. Plenty of great suggestions. So I'm very happy to see all of these suggestions. And we will now approach why quantum computing is so interesting. So what you can always do, and we will slowly get there now. So what you can do to speed up an algorithm is you can use a profiler and optimize individual statements. So a profiler would determine where you spend most of your time in your code, and you could try to tackle this. Sometimes there's like the 80-20 rule or 90-10 rule, which means maybe 90% of the time is spent in 10% of the code, or 80% of the time is spent in 20% of the code, and maybe you want to optimize those 10 or 20%. Don't do pre-evil optimize, or don't do premature optimization. Premature optimization is often evil and leads to lots of issues. So profiling later on can be a solution. Maybe choose a different implementation. We also got that suggestion, which is fine. We can do that. We can parallelize. So this was already suggested. Obviously, we could also use then hardware that is specifically tailored to parallelization. We can also improve the complexity. For example, in sorting, when you take an intro to algorithms, you learn you can do sorting in O of n squared. And for example, using a bubble sort, and if you have a faster sorting algorithm, faster in terms of the complexity class, you would have an n log n algorithm, such as merge sort, for example. You can use that. That's fine. And there are probably many other techniques how to optimize an algorithm so it runs faster. In order to take the most of this class, you should be familiar with the O complexity. So this notation that I have here, O of. Most of you are from the computer science department. Maybe again, send me like a green sticker if you're fine with the O notation. Send me a red sticker if you have never come across this. Because we also have students from engineering and other disciplines. So if anyone doesn't know the O complexity, just let me know. A very minor response for this. So O is a measure of complexity, and the complexity of an algorithm can be expressed in a mathematical way, where n is the input size to your algorithm, or the input size of the data you put in. And if you make n bigger, so you put in, say, for example, a longer list, how does the running time develop? You could have a linear algorithm, which is O of n, so it grows linearly. You could have a squared one, like O of n squared. So if n gets a little bigger, the running time gets much bigger. And we always try to reduce the complexity of our algorithm. I'm unable to provide an in detail revision of the O complexity now, since that's something we do in our computer science department in one of the introductory classes. You don't need to be an expert in O complexity for this course. However, if you have not come across the O complexity, please do some background readings or maybe check my algorithms and data structures course, which you can also find in Nextcloud, where we discuss these things, and you can find the past recordings, and this may help you to get a better understanding. So it's sort of an abstraction. We don't look at every instruction, but the main contributor to the running time of an algorithm, and then describe the running time depending on n, the input size. And we always aim for better complexity. So if we do sorting in O of n squared, imagine you put in 1,000 elements, then you would have a running time with a number of operations in around 1 million, can be more or less because this is just an approximation or a simplification, but in the order of 1 million, since n is squared. However, if you have, say, you put in 1 million elements and you have that squared, then you're in the range of trillions. And if you have a better sorting algorithm like n log n, this grows only very moderately, more than linear, but moderately, and scales much bigger, much better to bigger data sets. Now, what is the idea of quantum computing? With quantum computers, we want to be able to solve certain computational problems much faster than classical computers do. Much faster does not mean just in terms of a constant factor, like 10 times faster or 100 times faster, but solve computational problems in a much better complexity class. And on a quantum computer, for certain problems, we can take advantage of quantum effects. So we will also look in this course in quantum mechanics, and we can try to take advantage of quantum effects, in particular the superposition, which will allow us to do quantum parallelism. And quantum computers, if done right, can be inherently parallel, and we can solve certain computational problems in a much better complexity class. We will look into some of these algorithms in this course. One thing is very important: quantum computers are not in general better than other computers. Quantum computers, they are promising for certain specific computational problems, and you need to rethink the algorithm from scratch so you can take advantage of quantum effects in order to achieve quantum parallelism and thus get a major speed up. There are even some algorithms in quantum computing that give us an exponential speed up, which is enormous. There are others, they give us maybe a squared speed up, which is still great. And it's very important that quantum computers are not in general better than traditional computers, but rather for specific problems. And we still need to work hard on finding an algorithm there that allows us to do that. But all of this will be discussed in that class. And key to quantum computing is quantum mechanics. Maybe some of you have learned about quantum mechanics in a physics lecture or in high school when you finished high school and you had physics in your A-levels. We will not dig too deep into quantum mechanics. Rather, we will use it as a phenomena in quantum computing. So the physics part will be minor. We'll mainly see quantum computing as a generalization of the law of probability. So we deal with, all of you know, probability theory. We deal with real numbers that are between 0 and 1. And quantum mechanics is sort of, you can see it as a purely physics thing, but you can also see it in terms of probabilities. And quantum mechanics are essentially a generalization of the laws of probability. It works very different than regular probabilities, because in regular probabilities, we deal with real numbers between 0 and 1. But when we use complex numbers, we extend the possibilities of the law of probability, and that's why we generalize it. So we will deal with complex numbers rather than those non-negative real numbers. And we will work with the 2 norm. The term norm is something you should be familiar with from linear algebra. There's the 1 norm, the 2 norm, the 3 norm of a vector, and we'll be working with the 2 norm. If you don't know what the 2 norm is, it's fine. We will see all of this in that course, and we'll be dealing with complex numbers. And today there will also be a short revision on complex numbers if you're not familiar with them anymore. And there's a lot of extra text. So in the slides, I often put in some text that I don't read out. It's also meant for you just as a revision if you want to do some readings. But key to the whole course is quantum mechanics, but we will not look too much into it in terms of physics. Rather, we'll see it as a generalization of the laws of probability. And with that, we can then describe quantum parallelism plus other quantum effects and achieve quantum algorithms that run in a much better complexity class. And before we look into the organization of the course, I want to start with a motivation, an example of how quantum computing may be shocking to you now, but how it can be extremely positive and helpful. Imagine we have a set of n values. So our set is called V, and we have n values S0, S1, up and so forth, up to Sn minus 1. And we also have a condition, which is a function C, and I can pass to C some value Si, and the function, condition function, will either return 1 or 0. And there is a specific target value, which we call Sx. And if our input Si is equal to Sx, we will return 1. And if our input is different to Sx, we will return 0. So a very simple condition function. And now I want to know which of the values in V, which are the values S0 up to Sn minus 1, for which of them, if I put first in S0 in the condition, may return 0 or 1, and I want to find out which of these values in the set is the right one so that I find Sx. So what my goal is, find Sx, which is one of the values in V, and I want to know which of those values in V, and it's exactly one value for assuming this now, or none of them, which of those values is the one I want to find. And for now, I'm unable to sort them in some way. They're just values, and I don't know more about the condition function. It's just a black box to me. And I can try to implement this. So what I have now is my set V, which are values 0, 1, up, and so forth, up to 9. But it could also be other values. And there is some value Sx, our secret value. And I want to know which of them is the secret value. And I can try to implement this. So I built my set V, which for now, I just use the Python range. From the type, it's now a list and not a set, but it doesn't matter. So I use the range on n, meaning it's the values 0 up to 9. And I want to solve this. So I have my function solve it, and I go through all the values in X, and I check if that, so I go through every value in V, and I call it value I'm looking right now X, and I want to check, is the condition true for my value? And if the condition is true, I return the value. If the loop finishes, and I have never found a value that matches the condition, I just return false. And the condition looks like this. I pass a value I, and if I is my secret value, then I return true. Otherwise, I return false. So I've just implemented the problem from before. I want to know which of those values in V is the secret value I'm looking for. And I don't see what's the solution, so it's a black box. Now I ask you in terms of computational complexity. If I'm unable to bring in any structure in my set to sort of search it faster, I have to go through it naively. In classical computing, what is the complexity of black box search? It's O of what? If you have a suggestion, maybe without looking at the slides, send this in the chat. And I got already 2 answers, which are correct. It's O of n. Because in the worst case, and that's what the O framework refers to, in the worst case, I have to go through every element, and maybe the last element is the one I'm looking for, or I return false if none of them matches the secret value. So it's O of n, and it seems to be tricky to run this faster with classic computing. Probably none of us has any clue how that could be done faster with classic computing. And obviously, we could improve this in classic computing if we were able to bring in some structure. So if this was not a black box search algorithm, but if the values could be sorted and we knew maybe something that it's not so black box anymore, it could be run in O of log n, would be just a binary search. But since it's a black box search, I'm unable to bring in structure. So it's O of n. And now comes the scary part. In traditional computing, it's not just O of n, it's also omega of n. So O is the upper boundary, and then omega is a lower boundary. So I'm unable to do this faster than n in traditional computing, because I always assume the worst case. Obviously, in the best case, I just may be lucky and that the first or second or third attempt is the one I'm looking for. But with this O and omega, we always assume the worst case, not the best case, not the average case, the worst case. And in the worst case, I really have to try out every example until I get a solution or I know there's no solution. So traditional computing, it's omega of n. And now comes the shocking part. In quantum computing, this is O of square root of n. So with a quantum computer, I can solve this problem much, much faster. In fact, it's a squared speed up. So imagine you put in for n 1,000,000 with traditional computing. In the worst case, you have like 1,000,000 attempts. And with a quantum computer, you have something in the order of about 1,000 attempts. So it's a massive speed up, not exponential, but a squared speed up. If you feel surprised that this can be done with a quantum computing, maybe send some sticker or something that you feel this looks like scary or surprising that this is actually possible. And also a sticker that looks like impressed, also a good reaction. And when I saw this for the first time, I was shocked too. And in fact, this is the so-called Grover's algorithm. This is an algorithm we'll explore in a few weeks. But in order to understand Grover's algorithm, we first need to look into the mathematics needed. We will look into quantum mechanics. We will look into how to build a quantum computer. We will look into quantum operations. And then we will look into quantum algorithms. So it will take a few weeks until we're able to solve that mystery, how to get there. Because we first of all need to lay the groundwork. And there are also other quantum algorithms that even provide us with an exponential speed up, not just a squared speed up. If you want to buy a quantum computer, there are good news. Quantum computers are available today. They're on the market now for quite a few years, and you can buy from different vendors. There's IBM, there is D-Wave, and other vendors. But one thing they have in common, all of these quantum computers, at least most of them, and the ones that are professional, are relatively big and expensive. And D-Wave is, for example, one vendor of quantum computers. In fact, they call them so-called quantum annealers, which is sort of their own architecture, which we'll also discuss in a few weeks. And D-Wave offers multiple models. And a few years ago, they started selling the 2000Q. And the 2000Q is a relatively big machine that looks like that. It has 2048 qubits. So a qubit is a quantum bit. We use bits in traditional computing, and in quantum computing, we use quantum bits. And these are the fundamental units. We will also discuss later what they actually mean. And if you buy such a D-Wave 2000Q, you also need to cool down its chip. The chip is actually made of a metal called niobium. And if you cool niobium down to almost absolute zero, something around 15 millikelvin, which is 0.015 Kelvin, then you're close to absolute zero, and you're around like minus 273.135 degrees Celsius. So that is pretty cold. And if niobium is cooled down to that temperature, it becomes superconductive, and thus it will allow quantum effects. And you can then do on that chip quantum computations. If you want to buy such a machine from D-Wave a few years ago, the 2000Q, you could buy it. You paid around 15 million US dollars. Now they have more models and other models, but all of them are expensive. And also, if you run the cooling, this will easily cost you another $1 million per year. So it's a big expense. The hope is that in the coming years, those quantum computers become smaller and cheaper. So the approach to make hardware smaller and cheaper, that's something that works has so far worked well in traditional computing. And the hope is that that would also be possible with quantum computers to make them more accessible and more affordable. And they will also need more qubits. And there is good news. You can, if you don't have the funding to buy one of those machines, you can also use the cloud. D-Wave runs their own quantum computers in addition to selling them. And you can use the cloud to run your computations there. You get 1 free minute per month. You can buy more credit here in the cloud to run more quantum computations. And what you need to do is you need to type your code in the browser through some portal that looks a little bit like a Jupyter notebook, which is in Python, and you use libraries provided by D-Wave in order to access their quantum computer and to translate some of the code in your Python Jupyter notebook to low-level instructions in a quantum computer. And there's a good hint here in the chat. They also provide examples you can download, test, and play around. There are also things you can run locally on your computer in a simulator, so you don't always need to access the real quantum computer. You could also simulate it, which works okay for small problems. And there are also other vendors like IBM and so forth, and these are some of the things we'll be also exploring in this course. So you get a free minute per month. I had an example here, which was some demo, and if you run it, this took like 0.3 seconds. So we used around 0.5% of our monthly free plan. But it's fairly easy to create an account there. Feel free to try it and work with some of their examples. D-Wave has its own sort of more specialized architecture, which is a so-called quantum annealer. It's an architecture we'll talk briefly about in this course, because it has its pros and cons, but we'll also discuss other architectures later in this course. Now we'll talk a little bit about the organization of the course. What I always like in my courses is the map of computer science. So I don't know if you know this map. If you've taken one of my previous courses, you have seen that map. And the map of computer science provides us with a very good overview about the whole field of computer science. And in the beginning of a class, I always like to highlight where we are actually in this class, and I highlight, and then I zoom in a little bit to see what we are doing in this course. So the course is addressing multiple things. Obviously, quantum computing and parallelization, because quantum computers are inherently parallel, so we want to take advantage of that. The goal is to increase or to improve the computational complexity for our problems. So we're addressing computational complexity. We will work with algorithms that we want to speed up. So we look into the field of algorithms. We need to look into computer architectures, because quantum computers have a different architecture. With that, we can achieve extremely high speed ups. So we are in the field of supercomputing, and we will also look at various applications of quantum computing. For example, we'll look into applications to machine learning, information theory, cryptography, because quantum computers can break today's traditional encryption in the foreseeable future. We'll also look at the consequences of that. And we'll also look potentially a little bit into computational physics. So these are some of the topics that we'll look at, and overall gives us quite a good range of the map of computer science. And I just like highlighting this in the beginning of a lecture and to see what we are actually doing during the term. So the course is about, what I want to prepare you for a quantum future. So we'll have an introduction to quantum computing. We'll look into theory, and the theory will be quite tough, in fact. So we'll do a lot of mathematics, a lot of linear algebra, a lot of complex numbers, but we'll build everything from scratch. So it will be accessible. We'll also look into applications. And quantum computers today, they exist in practice, but a lot is still a theory, because we need bigger and more powerful quantum computers in the future. So I want you to be able to also apply the theory we discuss here to real problems, and that you have transferable skills. So you'll be able to join the change towards quantum computing, or the transition. And when you work in industry, maybe your employer will not buy a quantum computer so soon, but at least you'll be able to capture some potential and maybe see how the field is evolving and follow that change in the coming years, and be able to contribute and maybe find new potential for quantum computers. And as they become cheaper and more accessible, you can probably integrate them in your workplace too. But one thing is very important: quantum computers will not replace traditional computers anytime soon. They will rather be helpful for certain niche problems, but in computing as a whole, we will still have traditional computers for the foreseeable future, and the quantum computers will not replace them entirely, rather for certain specific problems only. So that's the goal of this course. And in order to take advantage of this course, actually, the prerequisites are relatively simple. Since we opened this course to students from many different departments, not just computer science, but also engineering, business, and so forth. And what you need is mathematics, in particular linear algebra. We'll do a revision today. And if you know about programming, this can be very helpful, but you don't need to be an expert programmer, because the course will mainly be mathematics, yet we want to be able to implement some of these things. And if you have an understanding of algorithms and data structures, That is very helpful too, like complexity and certain standard algorithms. But if you don't know that in detail, that's also not a big problem. Mainly, it's just maths in this course. And from there, we will explore the whole field of quantum computing. The course has the following structure. So we'll do lectures, which are 3 hours, so 180 minutes per week. So in some weeks, we don't do the whole 3 hours because it's just too much workload, and you also need to be able to revise it. So some weeks, it's maybe 2.5 hours, I don't know. We'll do lectures. There will also be some lab sessions during the term with specifically one lab problem where you can run some code on a real quantum computer. And we will show you that, and you can access a real quantum computer and run some computations there. The course is then 5 ECTS, 5 credit points. So 1 credit point is an average like 30 hours of workload during the semester. And we have 5 credit points, so the workload is about 150 hours of workload during the term. But most of the workload will be not a lecture, since a term takes 15 weeks. So the workload could be around 10 hours per week in average. Some of you will need less time, some of you will need more time, but most of the time you will actually need for revision, for doing further readings, doing some exercises, preparing for the examination. The examination will be a presentation, but I'll also say a few words on that very soon. But just going to the lecture is not enough, and you need to revise these mathematical things because they are quite heavy. And we'll start from scratch, but very quickly we will advance. So you need to be able to revise this, and don't underestimate the workload of this course. It's an advanced and relatively tough course. I provide my slide deck. Professor Kuhnhardt also provides his slide deck. I will also do quite a lot of calculations during the semester on my iPad and screen share the iPad with you during the lecture. So you'll see that. And all of this will be recorded. And the lectures will be for about half of the semester. So probably until mid or late November. We'll see how it goes. And then you have to pick a presentation topic that you want to present about. And the presentations will take place in January. And I've already announced the date for the presentations. It's in the iLearn course. It's January, in January, the Saturday, the 13th of January, we'll do these presentations. And the presentations will take place on site in Deggendorf. They will take place only on site. So the lectures are online, but the presentations, they are on campus in Deggendorf, and you need to be there, and there will not be any exceptions to present online or whatsoever. So all of this will take place on January the 13th. And you can totally pick the presentation topic you want to present about. And typically, most students have a more technical presentation, like an algorithm or some technical problem. But we also have some business students or students from business information systems. They can also present a more business-related presentation. And in the last few years, we've had really great presentations from computer scientists, but also from engineers. 2 years ago, we had, for example, a mechanical engineering student. He wondered about how you can actually manufacture quantum computers, and he gave his presentation about that, which was also really cool. So there are a lot of opportunities for the presentation, not just related to algorithms, but also maybe more to your field if you're, for example, from engineering or business. The presentations are done in groups, so we only accept groups of 3 to 4 students. So you're not allowed to do your presentation alone or with a second person, simply because this course is now so popular. And this year we have like 120 students signed up in iLearn, and that's why we need to enforce grouping for the presentations, which also makes it easier for you to discuss your work with others. And the group presentations will then be on January the 13th. So keep that day blocked for now. The schedule is, as I said, for half of the term, we will do lectures. We'll finish them end of November, early December. Then you select a topic, what you would like to present in your presentation. There are many opportunities for you to find possible topics. You could search for papers in Google Scholar. You can search in ResearchGate. You can also use a book, which I'll talk about in a moment. So there are lots of ideas that you can get what to talk about. And then sometime in early December, you need to briefly present your topic proposal. So what you would like to do in the final presentation. And I'll give you feedback on that, whether the topic is okay or not. So you and your group would just make such a topic proposal, which takes 1 or 2 minutes, and we'll discuss it. And then for the rest of the term, you would work on your seminar presentations, and in mid-January, you present them. And during those weeks you're working on your presentation, I'm also available via Zoom or in my office hours if you have any questions. So this is the schedule. There's also more information on how I mark the final presentation and how you get your mark. But all of this is something we'll discuss in December then, when we actually talk about your presentations. But the presentations will take 15 minutes and there'll be a 5-minute Q&A session. So overall, that's not too long. And how to get the mark, those of you who have taken courses with me before, they know how it works. Those who have not will learn this in December when we actually talk about the topic proposals. There are a few really good books that we'll be using in this course. We'll be using, for example, a book that is called Quantum Computing for Computer Scientists, which appeared in 2008 with the Cambridge University Press. Even though the book was from 15 years ago, it's still super helpful because the mathematics and the theory and the algorithms have not changed. The only thing that has changed now is that we have much bigger quantum computers available, because in 2008, that was largely a theory. So that part of the book is outdated, but the actual theory and algorithms, all of that is super valid. And a lot of theory, a lot of books on quantum computing are very difficult to read, because a lot of these quantum computing books are written for physicists. And since none of you studies physics as a major, it could be very difficult to read these books and papers. So the book Quantum Computing for Computer Scientists is actually super helpful. It looks like this. You don't need to buy it. I think I've made it available in the Nextcloud directory already. Otherwise, there are many ways for you to access it. And you can also buy it if you want, but you don't need to buy it. And the book is just super accessible because it makes the topic available for computer scientists. And the mathematics is more straightforward than if the book was written for physicists. And it's my absolute favorite book in quantum computing, and I'm sure it will be readable for you as well. There's also a book I published 3 years ago, Innovative Technologies for Market Leadership. It appeared with Springer 3 years ago, and one of the chapter authors also wrote a chapter on quantum computing. We'll talk about this chapter later. And there's another book that I just read during Christmas, during last Christmas, which is called Quantum Computing Since Democritus, written by Scott Aronson. The book looks like this. It's very important. It's not an arts book. This is refers to Democritus, a past scholar from the ancient times. And the Quantum Computing Since Democritus book by Scott Aronson is an absolute masterpiece. It also appeared with Cambridge, as I wrote here. And the book is probably the most comprehensive book I have ever seen on that topic, because it starts with very simple things like very fundamental maths like sets, then the whole issue of computational theories or the Turing test, the work of Gödel, then complexity issues like various complexity classes, randomness, and then slowly dives into quantum and quantum computing. The book is very difficult to read. So it assumes a lot of prior knowledge in mathematics, in computer science. I also struggled reading certain sections in the book and had to do some more background readings. There's not much maths in the book, but it's mainly text with little mathematics, yet the book assumes an extremely deep background knowledge in mathematics and computer science, and sometimes just assumes a lot of stuff, or is able to compress something that you would need like 2 weeks in a lecture to discuss, and it's just half a page. So it is very dense and compressed. So I also struggled with a few sections in the book. I need to do a few background readings. Yet the book provides a very, very good overview about not just quantum computing, but also fundamental issues in computational complexity and mathematics. So if you're curious about some really in-depth reading, I can highly recommend the book, but maybe only read the book once we have done this course, because it could be helpful as a primer. But you don't need to read that book in this course. So this is not something I would assume. Just if you're super curious and you want to learn more, take a look at the Scott Aronson book. It could be helpful. Something that is much more helpful for the course is the Quantum Computing for Computer Scientists book. Quite a bigger part of the slides is actually from the book, or content taken from the book, or compressed. And sometimes if you just look into the book in the same chapter, you would get further readings and maybe more detailed explanations than what I have written in the slides. If you look into the Nextcloud directory, there are recordings from last year. The course has not changed a lot compared to last year. What I have added this year is the Aronson book, just as a reference, and here and there a few slides, because one of the first slides today was about that quantum computing is a generalization, or sorry, quantum mechanics is a generalization of classic probability theory. That's a view from the Aronson book. I've also added something called mixed states, but that's just a smaller part. And there are certain sections I have extended, for example, the introduction, entanglement, the no cloning theorem. I've also extended quantum machine learning, because you can also do machine learning with quantum computers, and as usual, various minor improvements in the course. But probably 90% or 95% is the same as last year. So there are just a few things that have been added this year. I'll start asking, are there any questions about the organization of the course? If you have any questions, how the course will run, maybe just turn on your microphone or send a message in the chat. If there are any doubts so far, I'll just wait a second for you. So there don't seem to be any questions. And as usual, the topic of quantum computing is also reported about in the news. I sometimes read in newspaper articles that like quantum computers are the big thing and they would totally replace traditional computers, and that they are in general much better than traditional computers. Have you ever heard anything like this in the news? If so, maybe send a green sticker. If you have never heard anything like that, send a red sticker. So there are already a few green stickers. So that quantum computers will totally replace traditional computers and they are much better. That's something I read all the time, and it's just fundamentally wrong. Quantum computers are helpful for certain problems that we will explore in this course, but we also need powerful quantum computers to finally do that. And all of that is quite tricky where we are today. So they're not generally better, and they will not replace traditional computers anytime soon. Rather, they'll be employed for various niche domains. I also came across some article in a magazine called Foreign Policy, and there was an article last year in the summer. So I've only added this to the slides, I think, this year. I only saw this article a few months ago. As you know, there's a lot of fear about artificial intelligence, and there are all these perennial prophets that are warning that the end of the world is near because of AI. And I think which is largely just unrealistic. However, there are also now such people warning of quantum computers. And there are two researchers, Mr. Vivek Vatwa and Maurits Kopp. They both work at Stanford, and they wrote this argument in Foreign Policy why they believe that quantum computing is even more dangerous than AI. And they claim the world failed to regulate AI, and that's why we should regulate quantum computing. And the argument says that that's an expert's point of view on a current event. You can read the article on your own at home, so we don't read this article here in detail. Maybe read it until next week and let me know what you think about it. But it's a completely exaggerated article. And I checked these two people there. Like, one is a columnist in this magazine, and the other one is like a policy researcher. None of them has a background in technology, and now they are warning about quantum computing. That's something I also see with all these people who are warning that the end is near because of AI. Most of the people who are warning that the world would come to an end because of AI, they don't actually do AI. And it's the same people here warning now about quantum computing. And in this course, you'll actually see what quantum computing is, why it's very helpful, but also its limitations. And probably once this course is done, you will see that we will not that we're not doomed because of quantum computers. Rather, they are a very helpful tool. So sometimes I'm just very worried when I read such articles in magazines, and to me that's just scare tactic, and it's totally off reality. There is a very, very good article I want to share with you. It's called Quantum Technologies, and that's the article that appeared in my book that I talked about, my book from 3 years ago. This article is also uploaded in Nextcloud. And so in Nextcloud, there is a subdirectory for resources in this course. And I have uploaded this chapter, which appeared in my book, Innovative Technologies for Market Leadership. The chapter was not written by me, but by Daniel Akanine. Daniel Akanine is one of the CTOs of Microsoft, and he's one of my friends. And he wrote this book chapter. He's a physicist, but has been in IT for many decades, and is, as I said, one of the chief technology officers of Microsoft. And he wrote this chapter to make the topic of quantum technologies more accessible. It's something you can read at home to get a little bit of a better understanding of the history of quantum computing and what actually quantum computing is about. We'll talk about different effects like superposition, which is a highly parallel thing. There are also measurements and entanglement. This book chapter is something that can be a good primer for this course. So in this course, it's a very advanced course. I also expect you to do some readings independently. And this book chapter is written for managers and decision makers. So you can definitely understand it. And Daniel addresses not just quantum computers, but also other quantum technologies like quantum networks and quantum sensors and those kind of things, because Obviously, quantum cannot just be applied to quantum computing, but actually to many other things. And all of you are dealing with quantum technology every day. For example, flash cells that you have in a solid state drive or in a USB stick, all of them only work because of quantum effects. So you've been dealing with quantum hardware now for many decades, because without quantum effects, you actually couldn't run flash cells as they are built nowadays. So every USB stick, every solid state drive takes advantage of quantum effects. But quantum computing is something different. So we would use the quantum properties in actually not just store data, but to run computations. And I can highly recommend Daniel's book chapter. It's 9 pages, probably it takes you 1 hour to read. And it can be a good primer, especially concepts like superposition, measurement, entanglement for the remainder of this course. We will discuss and introduce all of these concepts in the coming weeks. But if you have a head start reading this book chapter, it can be very helpful. It's not ultimately necessary, yet it could be very helpful for you to read it. And the author is the real deal. As I said, Daniel is one of the CTOs of Microsoft. So I guess he is extremely qualified to write our book chapter. Now, in this chapter, we have a few things left that we should actually be covering, like the history of quantum computing, a little bit more of a comparison to traditional computing, applications and business potentials of quantum computing. You can learn this by either reading Daniel's book chapter, or at this point, Professor Kuhnhardt, my colleague, would actually be talking about those topics, but he's not with us today. Maybe some of you know Horst Kuhnhardt. He's one of our vice presidents in the university. So he's not here today. Most likely he'll be giving his lecture in 2 weeks' time from now, but I'll announce this beforehand, because I'm away in 2 weeks and probably he will step in and teach his part then. But we don't need this for today, because what we need today is actually mathematics. We will now look into the foundations chapter. We will look into complex numbers, linear algebra, and other things. And that's the remainder of what we're doing today. And as of next week, we will start using these math foundations in order to advance towards quantum theory. But first of all, we need to look at systems, and we will build quantum systems later. And then we'll look into quantum theory, and then we'll look into quantum computers. So once we're at chapter 5, we're actually back at quantum computers. And by then, Professor Kuhnhardt will have taught his part about the topics we have just mentioned. So that's not too important for today. And if you're curious, just read Daniel's book chapter and you'll be fine anyway with all of this. Are there any questions from you on what we have done so far? If you have a question, maybe send it to the chat. If you don't have questions, maybe just send a green sticker or something, so I'll see who is fine. Or if there are questions, send them to the chat. But I don't see anything coming in. So we'll be looking for today at the math foundations. Concretely, we will look at complex numbers, and then we'll look at complex linear algebra. Complex numbers are the first part, and after that, we'll use linear algebra. So we'll use vector spaces, which you typically do on real numbers, but we're going to do vector spaces and elements from there, like vectors, matrices. We're not only doing that on real numbers, but on complex numbers. And then we have all the math foundations we will need for the next chapter to build systems. And step by step, we're advancing then from those math foundations. Later, we will also, like in a few weeks' time, we'll look into algorithms. We'll look at theoretical boundaries of quantum computers. So when you hear things like quantum computers are extremely powerful and more powerful than everything else, well, there are some limits. We'll be discussing that. And in chapter 8, we'll also see how you can program a quantum computer and how to run this on a real, or how to run your code on a real quantum computer. And we'll also look into applications like machine learning, information theory, encryption, and so forth. Then I'm actually, I forgot one thing. I'm curious from which degree program you are. If you do like computer science or AI or cybersecurity, maybe just send this to the chat. If you are from a different degree program, also send this to the chat. So I'm just curious to see where you're actually from, and just to compare a little bit. So we have master students in AI, we have an electrical engineering student, we have a lot of students from AI, both in, or largely, I think, the German language program, business information systems, cybersecurity, regular computer science, masters in computer science. We also have quite some students from CALM this time, like the AI for smart sensors and actuators. We have exchange students, again, cybersecurity, and so forth. So overall, it's a very diverse cohort, and I'm aware that all of you have a different background in those things, and that's why we'll be exploring now the math foundations we will need for the rest of this course. But first, we'll do a 5-minute break, so we'll return at 3:06. See you in a moment. Welcome back from the break. And we will now look into complex numbers. That's a concept almost all of you should have seen before, definitely the computer science students, and especially the ones doing electrical engineering. I want to ask you, who of you is familiar with complex numbers? If you are, green sticker, or red sticker if you're not. Red sticker only if you have really never seen them. So not meaning you forgot them, but that you have just never seen them. And green sticker means you're sort of familiar or you have seen them before. And as usual, almost everyone has seen them, because if you study computer science or engineering, whatever, something you should have seen. Nonetheless, we'll do a revision because everyone may have seen them to a different extent. And I just want to make sure that we're all on the same page, so we can take advantage of complex numbers, which will be the very foundation of this course. Because as I said, quantum mechanics is a generalization of the laws of probability. We're using not real numbers between 0 and 1 in order to describe probabilities in this course. Rather, we use complex numbers, and that's why we'll need them all over the course, and they're the very core of quantum mechanics. As a motivation, say you have an equation that is something like x squared plus 1 is 0, and you try to solve this in a classical way. You would then say, well, x squared is minus 1, and that obviously is not solvable with the classic sets that you would use. So starting from school, you learn an increasingly more complex set of numbers, for example, positive numbers, which are integers 1, 2, 3, and so forth. We have the natural numbers, which are 0, 1, 2, 3, 4, and so forth. We have integers, which we sometimes also call whole numbers, which is z, which are positive and negative integers, and the 0. We have rational numbers, q, so we have m divided by n, where m is from z and n is from p, because we want to avoid dividing by 0. These are the rational numbers. And then we can again extend the space of numbers we are dealing with. And those are the real numbers, which are our rational numbers. And we union that with other special numbers that we cannot express as a rational number. For example, e, pi, e divided by pi, the square root of 2, which is also not rational. It's a real number, plus many other real numbers. And these are sets that you would learn in school or in, and they become increasingly more complex. If you're very curious about real numbers and why they are so special compared to rational numbers, that's also discussed in detail in the Aronson book. So feel free to read that, which can be, because this is that topic addresses some of the most fundamental questions in mathematics, in fact. And yet, solving something like x squared is -1, we are unable to solve with real numbers. So we can extend, however, the space of real numbers, and we can come up with a so-called imaginary number I, and I will help us to solve the x squared plus 1 is 0. So we can say x squared is -1, and we can then introduce I, and we can say that I squared is -1. And that's something you just cannot do with real numbers, because if you square a real number, like you square a 0, it stays 0. If you square a positive number, it stays positive. If you square a negative number, it becomes positive. But if we square I, then it's -1. So I is the square root of -1. And that's something you're unable to do with real numbers. But with this imaginary number, we're able to describe such phenomena. And we will now see we can actually work with I in a very interesting way. So you could wonder, what is I cubed? So I to the third. Well, you can say I cubed is I times I times I. I times I is I squared. And before we just said I squared is -1. So we can say here, I times I is our I squared, which is -1. And we have one I left, and -1 times I is -I. So I cubed is -I. So we can work with this imaginary number. You could also, for example, have something weird like this, a 1 divided by I, and that somehow looks really, really not neat. And a task for you is to think about how you can simplify this term, which is 1 divided by I, and we can simplify it. We can just multiply I in the numerator and in the denominator. So we multiply the numerator by I, the denominator by I. So the numerator is just 1 times I, which is I. The denominator is I squared, and that's -1. So I divided by -1 is just -I. In general, if you see complex numbers and you have an I in the denominator, doesn't look too good. It's correct, but I personally prefer to have the imaginary number at the top, not at the bottom. So if you ever see something divide by I, just multiply the numerator and the denominator by I, and it will certainly look neater. So I prefer having the I in the top, not in the bottom. And this imaginary number will now allow us to create a set of complex numbers. And the complex numbers are a set that extend the real numbers. And the complex numbers look different. A complex number is actually composed of 2 components. So a complex number Z is an A plus a B times I. And A and B are real numbers. So we call A the real number, or the real part of our number. Whereas, and there's actually a small typo I never noticed, so I'm deeply sorry. This shouldn't be a C, that should be a set. So A is obviously called the real part of set. So there are still sometimes some typos in the slides, despite having taught them for 2 years, which also means the students didn't read the slides properly in the last few years, because otherwise all the typos would be gone. If you ever see a typo in a math slide deck, let me know. And at the end of the course, so when the lectures have finished, I will once re-upload the slides. So because the typos are overall very little, but this should be a set. So A is called the real part of set, whereas B is called the imaginary part. And since always explicitly writing out A plus B times I doesn't look too nice, you can also just write A plus BI, where still A and B are real numbers and I is the imaginary number. Sometimes complex numbers are also written in a different way. Sometimes they're just written in such a way that it's an A comma B, it's a tuple. So you don't need to write out the I, but the A would then be the real part and the B would be the imaginary part. So the different ways how you can write out the complex numbers. What are complex numbers useful for? I'll start asking you, because we have students here from all sorts of disciplines. If you have used complex numbers before, maybe briefly write in the chat what you have used them for. And I'm curious to see what they can be useful for in your discipline. So I'll wait 1 or 2 minutes for your answers. To all the others, most of you study computer science. In computer science, the applications of complex numbers are quite limited. Yet, when you learn object-oriented programming, oftentimes you're asked to implement a class, and the class is then there to represent complex numbers, and you implement some fundamental operations, but this looks like it's sort of made up. It's not really an application in computer science. The applications for complex numbers in computer science are extremely rare. Largely, complex numbers are used in physics or electrical engineering to describe certain phenomena. And I'll see if anyone responds here in the chat. Like one student says they use in his discipline to describe electromagnetics. Another one talks about the modular forms and the Riemann hypothesis. Yes. There are certain things like electromagnetics, which can be described in terms of complex numbers. I think last year there was also a student from civil engineering, and they also use complex numbers to describe something in civil engineering. But in classic computer science, probably you don't see much, unless you look sometimes in computer graphics. You can describe certain computer graphics operations in terms of linear, in terms of complex numbers, or in terms of quaternions, which are even a further extension. And then you will definitely need complex numbers once you look into quantum computing. One other student says he uses this in fluid dynamics. Okay, so thanks for the different inputs. And I will switch now to my iPad, which just takes a short moment, and we will revise some key concepts of complex numbers. Just takes a second, and it's up and running now. And we will look at a few very simple problems or a few simple examples where we'll use complex numbers, so you're just familiar with them. So we will do additions and subtractions and multiplications. So all of this is something you have definitely seen once you learned about complex numbers, but we'll just do this now for revision. If you're curious about an in-depth revision, take a look at the Quantum Computing for Computer Scientists book where all of this is explained. So we can say we have a complex number, which is, for example, 3 minus I. So the real part is 3, the imaginary part is -1. And we have a second complex number, and we can say it's 1 plus 4i. And now is the question, what is C1 plus C2? When you add complex numbers, you add their real parts and you add their imaginary parts. So the real parts, 3 and 1, add up to 4. And the imaginary parts, it's -1 and 4, so it's plus 3i. You can also subtract complex numbers, so you would just subtract these components, which is, I think, fairly easy. But just that I'll make sure that we are all on the same page. We have another example, say C1 is -3 plus I, and we have C2, which is 2 minus 4i. I'll ask you what's C1 plus C2. If you have the solution, send it to the chat, please. And I'll see what your suggestions are. We already got the first suggestion here. -1 minus 3i, which is correct because it's -3 and 2, which adds up to -1. And -4 plus 1 is -3. So that's fairly easy. So now we know how we can add complex numbers. However, we can also multiply complex numbers. So we just phase this out. We just use the complex numbers from before, C1 and C2. And now we want to multiply C1 and C2. So we can try this. So C1 is 3 minus I, and we multiply this with C2, which is 1 plus 4i. And now we have these two parentheses, and we just multiply them accordingly. So the first part is 3 times 1, so 3 times 1. The next part is 3 times 4i. The next part is minus I times 1. So minus I times 1. And the last part is minus I times 4i. And now it's your task to simplify this. And once you have come to a solution, send it to the chat, please. So what's the result once we simplify this? Already got a suggestion in the chat, which is correct. So I'll do this slowly, step by step. So 3 times 1 is 3. 3 times 4i is 12i. We have then here a minus I times 1. So a minus I. And then this part here is a little bit more complex. So it's minus I times 4i. So it's minus 4i squared. And we'll write it out step by step. So 3 plus, we can already simplify this. 12i minus I is 11i. And this part here, I squared is minus 1, but then again minus 4, so it's plus 4, so it's 7 plus 11i. And we got multiple students in the chat who wrote this as well. So now we know how to multiply complex numbers. And there are a few more things, a few very essential concepts that we can look at. One is, for example, just check which one is next in my slides. One is the modulus, or absolute value of a complex number. So assuming we have a complex number, so we write out the modulus, or sometimes called the absolute value of a complex number. And we have a complex number that we call C, which is A plus B times I. So this is the standard definition of a complex number. We want its modulus, or its absolute value. So we put this around, and this would be calculated as A squared plus B squared, and we take the square root, and we want the positive value. And this would give us the modulus, or absolute value, or the length, if you see the whole thing as a vector. But we'll come in a moment also to the geometric representation. So I have one example here, say C is absolute value of 1 minus I. And I'm asking you, what's the absolute value or the modulus of C, where C is 1 minus I? If you have the solution, send it to the chat, please. We already got the right answer. So it's 1 squared plus minus 1 squared. So this is then 1 plus 1 and the square root. So it's the square root of 2. We can do one more. I now want the absolute value, or modulus, of 4 minus 3i from you. And if you have the solution, send it to the chat. So we got a few suggestions. So 4 squared plus minus 3 squared. So it's the square root of 16 plus 9, which is the square root of 25. So it's 5, which is correct. Has any of you ever worked in Python with complex numbers? If you have maybe a green sticker or something, I'll see if anyone of you has done this. Then just a few have seen it. I'll quickly switch to my terminal, and I can show you this. So we just use IPython, for example. And you have a complex number Z, and in Python, you can just say, well, it's, for example, 2 plus 4j. In Python, it's not an I, it's a j to express the imaginary part. And then you can see what's in Z. And we see it actually represents a complex number. And you can also try, I don't know, to square the complex number, so to multiply it with itself, and you get the result. Or you can use more complex numbers. You can put that into other functions and see what they return. So this is well integrated into Python as a native type, which is fairly helpful if you ever need to deal with complex numbers. Just as a quick piece of advice, if you ever come across this in Python, so it's just a J, not an I, which you need to remember, otherwise it doesn't work. I'll switch back to my iPad. And there is another very important concept in complex numbers. It's the so-called conjugate. And the conjugate is the following. If you have a complex number, like again, Z, which is A plus B times I, then the conjugate, which is often written with in a way like this would be A minus BI. So we're just flipping the sign of the imaginary part. And we also have a very simple exercise for you now. Say Z is 10 minus 2i. What is the conjugate? If you have the solution for the conjugate, just send it to the chat. So, and the answer here in the chat is correct. The real part doesn't change. We just flip the sign of the imaginary part. So it's 10 plus 2i. That being said, we have now looked into the most important concepts of complex numbers that I wanted to show on the iPad. There are a few more things I have prepared in my slide deck that I will share now with you. And then we have all the important concepts of complex numbers. So what we have just done is the addition and multiplication, the modulus or the absolute value, the conjugate. We can also express complex numbers in a geometric way in the so-called complex plane. So one dimension would be for the real component, one dimension would be for the imaginary component. And we can then visualize and represent a complex number as a vector. And then we have two other forms how we can express that vector, which is the polar representation or the Euler's formula. So we have a complex number here, which is AB. So we have A is the real axis, and the other axis is the imaginary one. And AB would then be plotted at A for the real part and B for the imaginary part. And then you can draw a connection between the 0 base and AB, so between the origin and our point. So we could essentially say that's a vector from the origin to our point, and the length of the vector is just the modulus or the absolute value. As you know, for a vector, how to calculate its length, it's just the same as we would calculate here the absolute value or modulus. There are in this, and that's the complex plane. Plane means the space we're working with. And what we can also see, there is an angle theta between the r-axis, so the real axis, and our vector r. And we can use this angle theta in order to represent our complex number in a different way. So our complex number is A plus B times I. We can also represent it by using this geometric perspective and we can represent A as R times the cosine of theta, and B can be represented as R times the sine of theta plus, and we add, or sorry, we multiply the I, which, because this is B, but it's B times I. In order to derive this, you just need fundamental geometry that you learn in school, cosine and sine. And now we see we have R and R here. So R is the length of the whole thing. And we can then just simplify the expression and say R times the cosine of theta plus I times of sine of theta. And this would be the polar representation. And another representation is the Euler's formula, or Euler's representation. And the Euler's representation uses the E, and it's E to the power of I times theta, which describes the rotation. And then you have the R, which is the length. If you leave R off, the length would just be 1. But since that's typically not the case, you need to multiply in front. And this is the Euler representation, E to the power of I times theta, which you have probably seen as well. Are you all okay now with this quick revision of complex numbers? If you're okay with complex numbers, green sticker. If there are any doubts, please send a red sticker or a question here in the chat. But it was anyway, for almost all of you, just a quick revision, which probably helps. When you study complex numbers, there are so many more things you can learn, like how to take roots of complex numbers and so forth. That is not necessary here for this course. If you ever need it, just look it up. But we've just looked at the most fundamental concepts. In order to test you a little bit, there are, you can find more exercises in the book, chapter 1 of the Janowski and Manucci book, which is the Quantum Computing for Computer Scientists book. Chapter 1 discusses the complex numbers in great detail with a lot of extra things and derivations and proofs. But we've just looked at the really essential stuff we needed to revise. There are a few problems that you can study and try at home. For example, you have this term 1 plus I divided by 1 minus I, and you're asked to simplify this. You can think about how you would maybe simplify something like that. Always try to simplify the denominator. Maybe that could help. You also find the solutions here in the slides. I'm not discussing these problems now. It's something you should just try at home, but it should be fairly straightforward for most of you. And there's also a solution here in the slides how to approach this. There's some other strange stuff you can then do with complex numbers, like what's I to the power of I? So you have this imaginary number and raise it to its own power. So not to the power of 2 or 3 or 4, but to its own power. Has any of you ever seen something like this before? If you have, maybe send a red sticker, sorry, green sticker, if you have ever seen such weird stuff, I to the power of I. It's also stuff I didn't really think about when I studied computer science. So when I was a first-year student and we studied complex numbers, I didn't think about such weird stuff. But there is a very good guy on YouTube. He makes a lot of maths videos. The guy is called Black Pen, Red Pen. So he's a professor somewhere in the US and makes a lot of videos on YouTube about maths. And he uses like a red pen and a black pen, just not to have one color, but multiple colors for illustration. And he often shows some weird math problems that he solves. So he's called Black Pen, Red Pen or something. Anyone knows this guy and his YouTube videos? If you do, maybe send like a thumbs up or sticker or something, not green or red. So there's someone who knows this guy. black pen, red pen. And sometimes I see some of these videos and I also really wonder how some of those problems can be solved. And I think he can solve them quite well and explain it well. And there I saw stuff like I to the power of I, and I wondered what is actually that. But it turns out raising I to the power of I is not that straightforward. What we need is we need to express the number in the Euler form that we have just seen. And then this is just the first step. We can apply the logarithm to a complex number and simplify this number by applying the logarithm to it. This is just an excursus. And then we can actually wonder about how we can raise I to the power of I. And there are a few steps you need to do by also applying logarithms to complex numbers. And if you're curious about how that works, take a look at this one here and try solving it. But here's the solution anyway. So this is some stuff I also didn't think about when I learned complex numbers, but I also got more aware of this from black pen, red pen, or other weird stuff like what is the ith root of I, so not the second or third root, but the root of itself. Then I don't know. If you're curious about how to do that, just take a look at the solution here. And if you've done the problem from before, this one is actually turns out to be straightforward. So this is some strange stuff I saw at black pen, red pen. Some of you said they know his YouTube channel. In that YouTube channel, he actually does even other really strange stuff, like what's the square, no, sorry, what's a matrix, or he takes a matrix and takes the root of a matrix, or the matrix root of a matrix. Has any one of you ever seen something like this in YouTube? If you have, maybe thumbs up or down if you have not. So that was some really strange stuff that was also new to me, how to do that. So you take a matrix and you can take its matrix root. You don't need this for this course, but it's explained in this channel by black pen, red pen. So sometimes if I can't sleep because I had too much stuff going on at home, I watch these videos, and each time I'm just amazed of how complex some of these problems look like and how straightforward the solution actually is. You don't need the black pen, red pen here for this course, not at all. Just if you like maths and want to see some strange problems, take a look at his YouTube channel. So I sometimes just do this if I can't sleep, or I don't know, I sit in a train or something and don't know what to do. And that's where I saw also this strange stuff here, like the ith square root of I, and you don't need it for the course, just it's fun. So now we have done the complex numbers, and I think we all deserve again a 5-minute break. So we'll be back at 3:48 to do the last step for today. So see you in 5 minutes again. So welcome back. Now that we have dealt with complex numbers, we can use them in quantum computing, but we also need to describe our operations in quantum computing in an adequate structure. So not just single numbers that we add up or whatever, but we actually represent quantum operations that we will get to know in a few weeks in terms of matrices. So we need vector spaces. We need to deal with matrices, with vectors, and with all of that. And when you have learned them in your first year, and I guess all of you have learned matrices and vectors, possibly even in school to some extent, you have also learned that actually we operate in so-called vector spaces. And we can write this as Rn, so just now, but real numbers. Rn denotes a Cartesian product, which is R, and so forth. And so you can have a structure in R3, for example, R5, whatever. And then we work in these vector spaces. So Rn denotes, first of all, the Cartesian product that you are all familiar with, which is also a foundation. And we have vectors, which are Rn. So for example, R5 means we have 5 elements in a vector. And with vectors, we can do various operations that we will soon revise in a moment. They come from vector spaces, so there are more fundamental concepts like the basis and the dimension of vector spaces. And we can also have matrices, which are 2-dimensional structures, and we can add them and multiply and so forth and do other operations that we will revise now as well. We will briefly revise the key concepts of this again for real numbers. And then we're going to put complex numbers into these structures, and we'll see how all of them behave. Most of these operations just behave exactly the same. However, there are some new concepts that we need to look at. And that's what we're now going to do for the last hour. And then we have all the foundations to build our quantum systems in the coming weeks, and then quantum architectures, quantum algorithms, and so forth. I will, for this, again, switch to my iPad. And we will now do something completely different. We will start with vectors and just need to find the right examples. So we have a vector, for example, V1 is a vector that has 3 elements, 1, 2, 3. And we have V2, which is, for example, 2, 0, and 5. And we can then add V1 and V2. This only works with vectors of the same dimension, and we just add these elements step by step. So 1 plus 2 is 3, 2 plus 0 is 2, 3 and 5 is 8. And this is how I have multiplied V1 and V2. I can, added, not multiplied, these two vectors. I can also use a scalar like 2 and multiply the scalar with V1. 2 is a scalar which would be multiplied with every element. So 2, 4, and 6 would be the solution. I can also wonder about the length of a vector. This is something we have already seen just before when we saw a complex number and interpreted that one as a vector. So we can have the length of, for example, V1, and that would be 1 squared plus 2 squared plus 3 squared. So this would be 1 plus 4 plus 9. So it would be the square root of 15. That would be the length of our vector. We can do all sorts of other things. So we can also visualize vectors, which works the best in 2D. We can also try to plot 3D on 2D, but after that, it gets more difficult to do all of that. There is also the inner product or dot product or scalar product of vectors. So we can have V1 and multiply it with V2. This is often called the dot product or scalar product, or more generically, the inner product. What we do is we build a sum of products. So we multiply each element with the corresponding element in the other vector, and then we sum these products up together. So it's 1 times 2 plus 2 times 0 plus 3 times 5. So this is 2 plus 15 is 17. Oh, and I had a mistake before, so thanks for pointing me to this. It's obviously the square root of 14. Thanks for letting me know. I had this in my mind, but somehow I wrote out 15. So thanks for letting me know. So what we've just done was the inner product, dot product, or scalar product, whatever you call it. There are more advanced concepts about vector spaces, like the basis and the dimension of a vector space. I will not repeat this now in detail. In case you ever need it, feel free to look up again what the basis is. In most cases, we anyway just use the standard basis, but you can transform from one basis into a different one. There's also the dimension, but that's something that you have learned in detail in your linear algebra lecture. And as there are vectors, there are matrices, and we'll also revise them briefly. So a matrix is from Rm times n. So a matrix has m many rows and n many columns. So m many rows, n many columns. And oftentimes matrices are written in terms of just checking how the book addresses this. So oftentimes we use a lower capital for a vector, and or a lower and a capital we use for a matrix. So M1 would be a matrix. Then we can have a matrix like 1, 0, 2, 5, and we can have M2, which we say is 2, 4, 1, and 2. And we can also multiply M1 and M2, and we just add these elements piecewise. So 1 and 2, it's 3, 0, and 4 is 4, 2 and 1 is 3, and 5 and 2 is 7. So I can add them, I can subtract matrices, I can transpose a matrix. A transpose, I would just show this at an example. So I can have M1 transpose, and the transpose means the first diagonal stays the same, and then I just flip all the elements along the or over the first diagonal. So I would just flip the 0 and the 2 compared to here before, and the elements in the first diagonal would stay. All these matrices here we have seen are square matrices, so the number of rows and columns is the same. Then there are more concepts like the determinant of a matrix. Are you all still familiar with the determinant? If you are, green sticker. If you're not, red sticker, please. Good. So I only see green stickers, so we don't need to revise that. Everyone is familiar with the inverse. Again, green sticker if you're familiar with the inverse. So, okay, just as a summary, if you have M and you multiply it with its inverse, you would have the identity matrix. And the identity matrix is a matrix where the diagonal is 1 and all the other elements are 0. That's the identity matrix, and M times its inverse, or the inverse times the matrix, the other way around, would lead to the identity matrix. Here now we've just done something. We've multiplied two matrices. So this is the multiplication. Are you also all still familiar how to multiply two matrices? Maybe again, green or red sticker. You don't remember this, or if you do, but with there again being only green stickers, I don't need to revise how the matrix multiplication works. Then I have another word. It's the trace. Who of you knows what the trace of a matrix is? Green or red? Please send red if you don't know. And this is one thing that many people don't know. The trace of a matrix would be the sum of the diagonal. So, for example, if I take M1 and I calculate its trace, then this would be a 1 plus 5. So it would be 6. So this plus this element. And it's a concept you can also apply to bigger matrices. You just add up all the elements in the diagonal. So this is the trace, which is a word that many of you have, or some of you have not seen before. It's also something we will need. And then there is this last, more complex topic of eigenvalues and eigenvectors. Green sticker, if you remember this, red sticker, if you have doubts about eigenvalues and eigenvectors. This is also a topic that is not always taught in such introductory courses. And as I see, it's also a problem here. I'll just briefly look here in my notes for an example, and then we can discuss that. For example, we have a matrix that would be, say, 4. So this is just the example from the book that I can come up with most easily. And what we notice here, we have this matrix, so 4, -1, 2, 1, and we multiply it by a specific vector, 1, 1. Then what's the result? So we have a 4 times 1 minus 1 times 1, which is then a 4 minus 1, it's a 3. And here we have a 2 times 1 plus 1 times 1. So that's also a 3. And the 3, 3 vector here is just a scalar product of the 1, 1 before. So we can write this out as 3 times 1, 1. So what we notice is we multiply our vector 1, 1 with this matrix, and its direction does not change. Only we have this factor, a constant factor eventually. And that's a special vector then of this matrix. And now we get into the concept of eigenvectors or eigenvalues. And what we notice here, we can also try to visualize this. So we have our vector, which is our vector 1, 1. And after we multiplied it, it actually became the vector 3, 3. So the direction of our vector has not changed, but its length has changed. And in fact, this vector would be called an eigenvector of the matrix, and that constant factor would be called an eigenvalue. So, and you can also write this out in a more mathematical way. If we have a matrix A and we multiply it with V, if we get then C times V, if that equation holds true, So A is our matrix, V is our vector, then V would be the eigenvector, and C would be the eigenvalue. And some matrices have eigenvectors and eigenvalues. Some matrices don't have this. And you probably wonder what's the property, or what is that property useful for? And that's often something you're not told in an introductory linear algebra course. Any one of you knows an application of eigenvectors and eigenvalues? If you know any application, maybe just send it to the chat. For whatever discipline, you just know some use case where you can actually use eigenvalues and eigenvectors in a useful way. Please let me know in the chat. And I feel in a lot of courses where you have an introduction to linear algebra and this concept is taught, also how to find eigenvalues and eigenvectors of a matrix, something we're not discussing now. If like you learn how to do it, what it is, but then there are often no applications and you're just forgetting the whole thing. If you have ever had such an experience as well, maybe send like a thumbs up that you learned this concept, but you didn't know any application, and finally it just seemed useless and you forgot it. If anyone had such an experience, maybe send a thumbs up. I think it appears, unfortunately, very often. One student here writes that he or she has seen this for geometrical orientation preserving, yes. And it can be used for a lot of different applications, but they are often not taught in the first year. There are various applications in machine learning, for example, PCA, the principal component analysis, in order to reduce the dimension of a data set. That can be done using eigenvectors. There are also other approaches how you can do such a dimensionality reduction. And in other fields, there may be other applications. We will also need this in quantum computing in a few algorithms later in this course to see and that's why I wanted to briefly revise the concept of eigenvalues and eigenvectors. If you're curious about how to find them, you need to solve a system of equations in order to determine the eigenvectors and then correspondingly the eigenvalues for the eigenvectors. It's something you can learn how to do it, but you don't need in this course, you don't need to manually find eigenvectors. You should just know what it is. One thing on top, if your eigen value is negative, say this was, for example, -2, all you would do is you're changing the direction of your vector. You're just flipping the direction, so it's just a negative value, and then this would still be an eigenvalue because you would and then just flip the direction and you would change the length here in the case 2. So here the corresponding eigenvalue would be -2 because we're just flipping the direction. So these are the fundamental concepts in linear algebra we need in this course. But so far we have done all of this for real numbers. And now comes the interesting part. All we have done here can also be done for complex numbers. And that's what we need in quantum computing. And I'll just briefly look for some examples in my notes that I use the same numbers as in the book, in case I want to do a revision. Say we have two vectors, v1, and v1 is now a complex vector. So it contains not real numbers, but complex numbers. The first entry could be 6 minus 4i, and the second entry could be 7 plus 3i. And we have a second vector, which contains also complex numbers, for example, 16 plus 2.3i, and a minus 7i. So this complex number here only has an imaginary part, and the real part is 0. Now we can, for example, calculate v1 plus v2. And all we're doing here is in each entry, we're just adding up these complex numbers. So for the first entry, it's 6 minus 4i plus 16 plus 2.3i. And for the second entry, it's 7 plus 3i minus 7i. And we can try to simplify this. So 6 plus 16 is 22. We have minus 4i plus 2.3i. So this is minus 1.7i. And we have the 7 here. And then we have 3i minus 7i. So it's minus 4i. So all the things we have done before on real numbers can be done also on complex numbers. And we're now in the field of complex linear algebra because we're applying linear algebra to complex numbers. If you, I don't know, I'll ask you, has any one of you ever done something like this before using complex linear algebra? If you have, maybe green sticker. If you have never done this, red sticker. Some of you have seen it if you have taken my algorithms and data structures course. We just had this outlook in the last week. But most of you have probably never done something like this. And when I did my bachelor's, I also never did anything like this. And I even met a lot of mathematicians. They have also never worked with complex linear algebra. But in fact, it isn't that difficult because we just plug in complex numbers rather than real numbers, and we just apply the same operations again. We can also then do all these other things like multiplication, transposing, and so forth with matrices for vectors. We've seen other things like scalar multiplication, the dot product. All of this works exactly the same with just with complex numbers, and you need to apply then multiplications and additions to complex numbers, not to real numbers, but it isn't that different. We can also have a matrix like matrix M1, which is a I'll just check for good numbers in the book that are maybe handable. I'll see if there's anything in the book. For example, we can have a 3 plus 2i. We can have a 0 here, and a 1 here, and a 4 plus 2i. And we have a matrix 2, where we have a 5, 2 minus I, a 0, and a 4 plus 5i. And I want to know from you what's M1 plus M2. If you have the solution, just send this to the chat, please. I'll give you a moment to do these additions, to add the two matrices. And once you have a solution, send it to the chat, please. So we already got a few submissions. So 3 plus 2i plus 5. So 3 plus 2i plus 5 is the first element. The next element is 0 and 2 minus I. So that's fairly easy. 1 and 0. And the last one here is 4 plus 2i plus 4 plus 5i. We can simplify it again. So that's 8 plus 2i, 2 minus I, 1, and then 8 plus 7i. So you see, this is fairly straightforward. We just use complex numbers, not real numbers anymore, to do all of this. You can also transpose complex linear structures. So if we have our matrix M1 from before, 3 plus 2i and 4 plus 2i, they just stay. The 1 comes here and the 0 there. So we just flipped them, and overall, that's not too complex. I'll just briefly check. Inverting is also possible. The trace is also possible. The determinant. The only thing that gets a little bit more tricky, if you really ever want to calculate the eigenvectors and eigenvalues of matrices that contain complex numbers, that's usually more tricky than if you do it with real numbers. But in this course, you don't need to calculate them manually. If you ever had to do this, you would just use a library or some software tool to do it for you, because it is more tricky to calculate the eigenvectors of matrices that contain complex values. But doesn't really matter for this course how to do this specifically. With that, I'll switch back to my slides in a second, and they're ready. So we'll be here soon. So we've seen all these concepts for real numbers and for complex numbers. We've also seen now how to add and so forth, vectors, matrices. There are, however, some new concepts that only exist when you use complex numbers, so when you use complex vector spaces. And there are a few new concepts that we will look at. We will look at the conjugate matrix, the adjoint matrix, and we will look at unitary matrices. Those of you who have done my algorithms and data structures course, they saw this very, very briefly. We'll discuss it today here for everyone. And then there is one more concept that is probably new to almost everyone. It's the tensor product. And then we have all the math foundations we need for the remainder of the course. We have seen the conjugate today in terms of complex numbers. So the conjugate was the operation which just flipped the sign of the imaginary part in a complex number. We can also apply the concept of conjugate to a matrix. So we have a matrix A, and its conjugate is denoted as A bar. And what it does is we apply the conjugate operation to every element. So we have a matrix A, which is now a square matrix, 2 times 2, and it has its entries A, B, C, and D. And I want the conjugate matrix, and then I take the conjugate of A, B, C, and D. They don't move. I just take the conjugate of every entry. We can try this out with an example, and maybe don't look into the slides, but quickly try it for yourself. So the first entry is 6 minus 3i. The next entry is 2. The next entry, 9i. And the last entry is minus 2 plus 4i. And what I want from you, please, without looking at the slides, what's the conjugate of the matrix? You just apply the conjugate to every entry. And once you have your result, send it to the chat and we'll compare briefly. We got a few suggestions, and it's straightforward. So the first element would be then 6 plus 3i, because we changed the sign of the imaginary part. Second element doesn't change at all because it's only a real part. The next one is minus 9i, and the last one is minus 2 minus 4i. So this is the conjugate matrix of a matrix, which is straightforward. And that's a new concept, because if you only plug in real numbers, you can't get the conjugate. And there's another new concept, it's the adjoint matrix. And the adjoint matrix is written as A, and then this kind of cross, and that's pronounced an A dagger, because it's not really a cross, it's more like a dagger, so something like a little bit bigger than a knife. And this is the standard notation for this. So it's not a transpose, very importantly, it's a dagger. And this A dagger has a specific function. If I have, again, a square matrix, A, B, C, and D, and I apply the dagger to it, or the adjoint operation, then I'm doing two things. I'm doing a transpose, so I'm flipping C and B, these two are flipped, but in addition to the transpose, I also do the conjugate operation on every element in here. And again, our matrix from before, we had previously applied the conjugate operation. Now we apply the dagger, the adjoint. Pretty much the same result as before, but we also do a transpose. So the 2 and the minus I, they flip, because the 9i was here. It becomes a minus 9i because of the conjugate, and it goes up here and flips with the 2 because of the transpose. So the adjoint operation is a transpose and a conjugate operation. So it's two things on the matrix. You probably wonder, what is all of that useful for? And here comes the important part. In quantum computing, we will express our operations through matrices. The fundamental computing operations in a traditional computer are logic gates, like an AND, an OR, a NOT, and from that we can build everything in logic, or at least in binary logic. And our quantum computer will also have fundamental operations. They will not be ANDs or ORs, they will be different operations, but these operations will all be expressed by matrices. And there's a special category of matrices, which are so-called unitary matrices. And the unitary matrix is the following. If I have a matrix U and it is unitary, then the following holds true. I have U dagger, so I apply the adjoint operation, the transpose and the conjugate. Then I have U dagger, and I multiply this with U. And if that leads to the identity matrix, then U is unitary. The same if I apply or if I multiply U with U dagger. If this condition holds true, then U is unitary. This may look very similar to you with the inverse. So the inverse is an operation you have all learned a long time ago. Obviously, inversion and the adjoint are two totally different things. They only have in common that if you apply U and multiply it to its U dagger, or U multiplied with its inverse, that it leads to the identity matrix. But yet the inversion and the adjoint are two completely different things. And we don't need inversion that much in that course. Mainly we'll be working with the adjoint. And we can also briefly take a look at a matrix that we will come across in a few weeks again. And that matrix is called H for the so-called Harder-Matt gate. Harder-Matt is, the Harder-Matt gate is a very fundamental operation in quantum computing, which creates a superposition. A superposition is a parallelism, which we will also discuss. And there we will come across this H again, you don't need to remember it now. It's only something as a preview. And the H is in fact unitary. So if we apply the dagger to it, it actually doesn't change at all, because there's just a 1, 1, 1, -1, and the transpose doesn't change anything. And since these are only real entries or real components, the conjugate also doesn't change anything. So H and H dagger are here just the same by accident. And if you multiply them, then we get the identity matrix. And you probably wonder, what is that useful for? And the reason is, in quantum computing, and that's only a preview now, we'll deal with reversible computing. Reversible computing means you apply an operation to, say, two variables, and you apply that operation again, you would undo it. Something that you know of that sort, say with one variable from binary logic, is the NOT gate. The NOT gate, you just flip the value and you apply the NOT gate again, you flip it again, so it's undone. But there are other operations in binary logic that you cannot undo, like an AND gate. Like you have an AND gate of two variables, you have one result, and you cannot just apply that again and undo the whole AND because you have a loss of information. And in quantum computing, all of our operations, they need to be unitary. There are certain theoretical reasons for this that we will also explore in a few weeks. So we always need to work with unitary matrices as our base operation so we can undo them. And we use that computing, the concept of uncomputation, which will help us also to speed up algorithms to some extent. But that's something we will see. So only that you have a motivation to see why we actually need the concept of unitary matrices, and this matrix H will be explored in detail in a few weeks. There is one last mathematics concept left for today, and it's the so-called tensor product. The term tensor is something that many of you have previously come across, I guess, when you deal, for example, with TensorFlow. And who of you knows what a tensor is? So I'll just skip the slide from before. If you have a suggestion what a tensor is, maybe send it to the chat and I'll see if I'll agree or if the others agree. So what could be a definition of what a tensor is? I'll wait a little bit and see if there are more suggestions. So in classic mathematics, there are some constraints on what a tensor is. But in, say, AI and machine learning, it's been established that, say, a tensor of degree 1 would be just a matrix. A two-dimensional tensor would be a vector. The one-dimensional would be a vector. Two-dimensional would be a matrix. But then you could also go in higher dimensions, like three-dimensional, four-dimensional, and tensors would be higher dimensional structures, so like a matrix, but just in higher dimensions. This is how it's interpreted in machine learning and AI. If you talk to mathematicians, for them, there are still certain constraints on tensors, but that doesn't matter for us here today. And so all of you have heard about tensors, say, through TensorFlow, a very famous deep learning library. And the concept of tensors is also something we will need. We'll probably deal only with lower dimensional ones in this course, but we will need a concept which is a tensor product. And I'll share my iPad again. Sometimes this app is just hanging and it takes a moment to come up. We will now look at a tensor product, and a tensor product is written this way, of two vector spaces V and W. And I'll quickly show you how it's defined, say for small matrices, and then we'll see what it's actually useful for. So we have two matrices, V and W, and we will calculate now the tensor product. So we have A11, A12, A21, and A22. And we have the same for B11, B12, B21, and B22. And the tensor product eventually for these matrices creates a larger matrix, which would look something like this. We would have our A11, and then put our B here, B11, B12, B21, and B22. This would be then the first square of our final matrix. And we have another square here and another one there, where we have our A12. And again, the matrix B, so B11, B12, B21, and B22. We would be doing the same down here for A21, dot, 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 just the same matrix B and A22. And here A is just a scalar that we would multiply with every element. And if we write that out, we would come to a new matrix. So we would have our A11 times B11. This would be the first entry. Then A11 times B12. So just, this would be that, this would be that, and so forth. We would have our A11 and times B21 and A11 times B22. This would be now the first square, and we would continue in these other four squares, and this would finally be our matrix. If you're curious about what this looks like in a written form, so I don't need to just repeat this on the iPad, it's all shown here. This is just what we have done, which I was too lazy to write out now entirely. And the tensor product, it will be a very important concept for us in order to compose multiple spaces, and that will be needed in order to build larger composite systems, which we will apply also to quantum. And like this, we can compose quantum systems, and that's something we will later need when we have multiple qubits that would work together. So as I said before, a qubit is the fundamental unit in a quantum computer. In a traditional computer, we have the fundamental concept of a bit. A bit is always either 0 or 1, but a qubit or quantum bit can be in both basis states, 0 and 1, at the same time with a certain extent, a so-called amplitude. So it can be in both basis states at the same time with a certain proportion. That's what we call the amplitude. And that amplitude will be described by a complex number. And when we have multiple qubits that should work together, and we want to describe that, then we need a tensor product in order to describe all of this in matrix form. It's something we will see in a few weeks. If you want to learn more about complex vector spaces, take a look again in the book Quantum Computing for Computer Scientists, the Janowski and Manucci book, where all of these things I have just discussed are again explained in much greater detail with a lot of proofs and further explanation. But what we did today was we had an introduction as a motivation also to quantum computing. Like we looked at briefly the idea of Grover's algorithm, that we can solve this black box search much more efficiently. And we looked a little bit at how expensive a quantum computer is. We looked at the structure of this course. And then today we looked at the foundations. So we looked at a revision of complex numbers, as well as we did a revision of the key concepts of vector spaces, and then applied complex numbers to all of this to discuss complex vector spaces. Now these foundations are done. And next week, we will look into systems. We will describe so-called systems, how states in a system evolve, and we will start initially with deterministic systems and then probabilistic systems. None of that is important for quantum computing yet, but we will establish a formalism using matrices and vectors and all these concepts we saw today. We will start with deterministic systems, then probabilistic systems, and then we generalize this even further to look into quantum systems. And then we have multiple quantum systems and we want to assemble them. And for assembling or composing, we need the tensor product. That's essentially what we will do next week. And then we have laid all the foundations to use our matrices and vectors in a specific way. That's why today we started with vectors and matrices and complex numbers. Next week, we'll use them to build systems, and eventually we'll be able to compose or assemble quantum systems. And then we have all the groundwork to look into quantum theory, and a few weeks later, dive into quantum computing. So it will take a little bit for us to get to quantum algorithms and the theoretical boundaries of quantum computers, because step by step, we need to establish this formalism to always do all of these operations in terms of matrices and think in our states in terms of vectors. And then in the coming weeks, we'll get closer to all of this, and it will be all more related to computing, because so far we're just building the foundation for all of this. And your presentation topic is something you need to know in like 2 months. So all of this will become more clear in the next 4 to 6 weeks, and then you'll also be fine with choosing a presentation topic. Are there any questions from your side about today or the next steps? If you're okay, maybe green sticker. If you're not okay, red sticker. If you have some old red sticker, either delete it or refresh it. And there is a question if I could explain more about the presentation topic. Well, it must be some presentation related to quantum computing. It can be some specific quantum algorithm. It can be some specific architecture that is now on the market. It can be how you apply quantum computers to machine learning or how you crack encryption. Some students are more from engineering. They could also think about maybe how to apply quantum computers to their discipline, how to manufacture quantum computers. Others are from business. They could think about a business use case, business potentials. There are also in this book, which is the Janowski and Manucci book that I mentioned, the Quantum Computing for Computer Scientists. There's also a chapter at the end with possible topics for student presentations. So starting page 360, you can take a look at possible student topics for presentations. Go through that. Maybe there's something, but you don't need to make that decision today. These are only suggestions. Sometimes students pick some topics from here, but there are also new developments like new quantum computer architectures or specific algorithms. But if you're so far curious about potential topics, maybe just take a look at the book. It doesn't need to contain novelty. You would just present something in the something from the state of the art. And there was another question here about the score page, how I come up with the mark. This is something that the question that I don't want to answer now, because how the presentation will be marked is something that is important once you know your topic. And I'll also provide more insights about the marking of the presentation, but I'll explain this in December, because so far we're just too far away to talk about marking. But the presentation doesn't need to include novelty. It can be about the state of the art, some papers, some process. Obviously, if you present something novel, and there were students in the past who did that, who implemented some quantum algorithm or applied it to some specific problem, that's great as well. All right, so I don't see any further questions. So I know today it was a lot of maths and revision, but we'll need this. Make sure for next week you're okay with all the math we did today when we apply this to deterministic, probabilistic, and quantum systems. And then we'll get closer to quantum computing. So see you next week at 2 o'clock here again, and have a great weekend. Bye-bye.